Let's jump into a discussion of classification methods. This will be the first of 3 lectures on how you build a classifier or predictor for use in medical applications. So if you'll remember when we talked about prediction versus inference, a prediction problem is one where we collect a population of individuals, we sample from them using probability to get a smaller subsample, then we use the data in that subsample to construct a function f. The function f uses one characteristic of the people, in this case whether they're wearing a bow tie or not, to predict another characteristic of the people, in this case the color, green versus purple. So we observe in our small subsample that all of the people that have bow ties are purple, and most of the people that don't have bow ties are green. So we create a prediction function that says, if you have a bow tie, then you're a purple meeple. And if you don't have a bow tie, then you're a green meeple. So this prediction function is then used in various applications to make decisions, say, for the medical treatment of these meeple. So there's 3 parts to constructing a prediction function like this. There's the data that we actually use to build that function. There's the model itself and technically how you actually construct a function that makes the prediction. And then the third part is the application. Actually, how do you use the predictions that are created by that model? In this lecture, we're going to focus on the data. So this is our setup where we have a population and we've sampled from that population using appropriate probabilistic sampling, and we've got our subsample, then we can construct our function. But there's a couple of different ways in which this could go wrong, and there are things that you should be thinking about whenever you're evaluating how well a prediction function could do. Because while it's an assumption that the prediction function itself is unbiased, the data that could be put into that prediction function could suffer from a number of different problems. So the first example of a problem that could occur is that we could sample in a biased way from the population when we're creating our subsample. So for example, in our general population, you can see that when you're green, most often you're not wearing a bow tie. And when you're purple, you're most often wearing a bow tie. But imagine, due to some circumstance, whether it's accidental or on purpose, we've collected a small subsample of individuals where the opposite relationship is true. So in general, it looks like the green meeple are wearing bow ties in the sample, and then purple meeples are not. Well, we're building our prediction function based on that subsample, and so our prediction function might say, if you have a bow tie, we'll predict that you're green, and if you don't have a bow tie, then we'll predict that you're purple. This is, of course, the opposite of what the relationship really is, so this prediction function won't work well when applied to a new person that comes in to the clinic. A widely known example of this in the United States is the case of automatic sentencing for recidivism in the United States. So the idea is that you could use characteristics of people to predict how likely they are to recommit a crime. And by predicting how likely they are to recommit a crime, you could determine what sentence they should get. Well, the data that have been collected that are used for making these predictions are based on historical arrest and historical recidivism records, which have all sorts of cultural, historical, and sociological biases built into them. So for example, 2 individuals, one African American and one Caucasian, who committed the same crimes, had the same characteristics and profiles, might get wildly different sentences. So this is because the training data that we've collected have biases built into them. It's not the algorithm that's the problem, it's that the data themselves have biases built into the data. So the first thing to think about when evaluating a prediction model is to determine, are there biases that are built into the way that we've sampled the data that we're using to build that prediction? The second problem could be that you've picked the wrong features to predict with. So in this case, I've got a sample where I've got 2 characteristics that I could use to predict the color of the meeple. I could either use whether they're wearing a bow tie or not, or whether they're wearing a hat or not. And so it turns out that whether you're wearing a hat or not is unrelated to what color you are. But in this subsample that we've collected, it looks like wearing a hat is predictive of what color you are. The purple meeple in the sample have hats, and for the most part, the green meeple in the sample do not have hats. So if we pick the feature of a hat, we say, we'll predict that you're purple if you have a hat, and we'll predict that you're green if you don't have a hat. Because of this choice of the wrong feature, we would see that in a new sample, there would be a bad prediction accuracy of using this function. And it's because you're about equally likely to have a hat on if you're a purple or green meeple. And so this is a case of where we picked the wrong feature to predict with. One way to sort of detect this in observed papers is to ask yourself, is it reasonable that the features being used to make the prediction should predict the outcome? Here's a classic example. In this plot, I'm showing on the x-axis the chocolate consumption in kilograms per year per capita for various different countries. And on the y-axis is the Nobel Prizes per 10 million in the population. And so you can see that there's a high correlation between these two numbers. In other words, we can predict the number of Nobel Prizes that come from a country based on how much chocolate they eat. We don't really believe that the amount of chocolate consumption has anything to do with whether people win Nobel Prizes or not. There are probably other underlying factors that make this relationship hold true. So if we build a prediction that's based on chocolate consumption for how likely it is for a country to have brilliant genius scientists, in general, that prediction model will not likely hold in new samples because that variable, chocolate consumption, is actually probably not that predictive of the outcome that we care about, which is how many genius Nobel Prize winning scientists we produce. So asking yourself, is the feature we're using to predict chocolate consumption really related to the outcome that we're trying to predict, Nobel Prizes? And if it's not, then be skeptical of that prediction function because the underlying data is maybe not appropriate. The last case assumes something about the population itself. So imagine that we've built a prediction function and we've done everything appropriately, but then over time, the population itself changes. So this can happen all the time when there's some characteristic of the population that's evolving over time, whether that's access to information or whether that's the way that people are consuming food or the way that they're exercising. If the population is changing over time, our predictions may no longer apply. A classic example of this is that Google Flu Trends was a prediction algorithm that used Google search terms to predict how many cases of the flu there were at any given week in the United States. And when the model was built, it very accurately predicted the number of flu cases according to the CDC model, which used more on-the-ground data going hospital to hospital to collect that data. But over time, as people's search terms changed and as Google changed its search algorithm, then the predictions started to diverge from each other. The prediction algorithm didn't change, the input data changed because the population of searches changed over time. So while the algorithm wasn't broken, the population itself was changing and therefore the prediction worked less well. So we've talked in this lecture about the different ways in which the data might be biased. And so one of the things you should be thinking about when evaluating any classification, machine learning, or prediction problem in the medical literature is, how sure are you that there aren't biases built into the way the data that are sampled? How representative are the sampled training data of the population that you care about? And are they picking the right features to make the predictions with? In the next lecture, we'll start to talk about the function used